Hello students, and welcome to another edition of this series of physics lectures. So we have been looking at the review of the key elements of class 11th physics. We have started with this series of lectures for the revision of vector algebra in basic calculus and its applications in physics. So let us continue with that. So this is the fifth and final edition of this particular section, where we are looking at a review of calculus and vectors. So in the previous 4 sessions, we have looked at the basic concepts of vectors and vector algebra. And in the last lecture, session number 3, we have looked at some of the key elements of differentiation, derivative, and its application to physics type of problems. Okay. We will start today with a little bit ahead about differentiation. We will look at the concept of maxima and minima of a function from differentiation. Okay. So we will look at application of derivative in the context of maxima and minima of a function. So again, we will focus more on the type of applications that this gives us in physics. Okay, but let's look at the essential concept first. So supposing we have a function which is what we call non-monotonic, that is, it's not just increasing or just decreasing, but it has a behavior where the function increases with respect to x in certain part of the domain, and then later decreases with respect to x also in a different part of the domain. Okay, so let's say the graph of this particular function we are talking about, the graph has a nature which is something like the one I'm drawing over here. It need not be in the same kind of order. It can be a different order also. It could be first decreasing and then increasing or whatever, but it has a nature which is what we call non-monotonic. That means the function is neither only increasing nor only decreasing. It is alternately increasing and decreasing in different parts of the domain. So if that happens, then based on, so this is the graph of the function y equal to fx, and fx you can see is a non-monotonic function in nature. That means y increases with respect to x for a certain codomain or part of the domain, and y decreases with respect to x for certain codomain or subset of the domain. Okay. And further, when that happens, then the function always has what we call turning points, where the behavior of the function changes from either increasing to decreasing, in which case that turning point becomes a point of local maxima. So let's say that point is A over here, and there will also be another type of turning point where the behavior of the function changes from decreasing to increasing. Okay. So at that particular point, the function will have what we call a local minima and a local maxima. So we will look at the definition of these two things also next. So this type of a function may have what we call turning points at x equal to a in this particular case that you're seeing here, and x equal to b, where the behavior of the function is changing from an increasing function to a decreasing function or vice versa. Okay. So also if I were to label the initial point in the domain as, let's say, x1, and the final point in the domain, or the boundaries of the domain as x1 and x2, in this example, what else we can observe is that the function is increasing in the region x1 to a, and again in the region from b to x2, but in between in the region from a to b, the function is in the interval from a to b, the function is decreasing. So we can also observe here that in this particular function here, y increases with respect to x for x belonging to that part of the domain, x1 to a, and again union with p to x2, whereas y is decreasing with respect to x for x belonging to the part of the domain which is in between a and b. Okay. So just take a look at the graph again and understand these two statements. Okay, the function is increasing in nature. That is, if I increase x, y increases, and vice versa for decreasing for these two parts. Okay. So in terms of derivative, what that will mean is that if you draw a tangent, okay, at any point over here, for example, if you draw a tangent at any point in this region between x1 and a, that tangent will have a positive slope. Again, if you draw a tangent at any point over here, you can see that that tangent will have a positive slope. Okay. Whereas if you draw a tangent at a point like this now, you can see that it will have a negative slope. Okay. So remember that tangent has a slope equal to the derivative of the function. So in terms of derivative, what that means is that y equal to fx has a positive derivative, that is dy by dx, or derivative has a positive value for the part of the domain where the function is increasing. Okay. Whereas the same function has a negative derivative, that is dy by dx will be negative in value for the part of the domain between a and b. So this is one way of understanding the application of derivative in context of behavior of the function, whether the function is increasing or decreasing. We can understand that by looking at the algebraic sign of the derivative. So let's understand this in context of a simple example problem. Okay. So suppose we have a situation where a particle moves along the x-axis, okay, such that its speed, or you can say its velocity, but in one dimension is magnitude of velocity, okay, expressed as a scalar, is given by, say, v is equal to this function, where t is time in seconds and v is velocity in meters per second. Okay. Now we want to find the interval of time for which the particle is accelerated, that is v is increasing, and for which the particle speed is decreasing, or it is decelerating. So the velocity is decreasing in magnitude. Okay. And let's say that this particular function that is given to us now, it is for a fixed range of time. It's not like it is exactly for okay. Let's just make a correction here. Instead of 2t square minus 60, we'll make it 6t minus 2t square. Okay. And let's say the time that we are taking is from 0 to 3 seconds. It's only between 0 and 3 seconds. Okay. So we have to understand this thing. Okay, find the interval within this time between 0 and 3 seconds for which the particle is accelerating or its velocity is increasing in magnitude, or consequently it is decreasing or its velocity is decreasing in magnitude. So let's understand this. So here we will use the relation that the acceleration is dv by dt is equal to the rate of change of v with respect to time. Okay, so that means that dv by dt being positive, that means v is increasing, and dv by dt being negative, it means v is decreasing. So this implies that the particle is in accelerated motion, and this would imply that the particle is in decelerated motion. So this is the implication in terms of one-dimensional motion. That is motion along a straight line. This is how we describe the situation. Okay, so you can see here that since it is given to us that v was 6t minus 2t square, following the correction that I made. Okay, so it means that dv by dt is equal to 6 minus 3t. Sorry, 6 minus 4t. Just differentiate this. Okay, so let's do this step by step. So differentiation of 6t minus 2t square. So that will just become 6 minus 4t. Okay, or we can write that as 3 minus 2t. So we can see that dv by dt is positive, implies that this thing should be greater than 0. So that implies that time should be less than 3 by 2 seconds, or t should be between 0 to 1.5 seconds, okay, for the dv by dt to be positive. So what that is telling us in context of the problem is now that this is the interval of time for which v is increasing or it is having accelerated motion. Okay. And similarly, dv by dt being negative means that this should be less than 0. So it tells me that t should be greater than 3 by 2 seconds. So remember, overall my domain was that the time was from 0 to 3 seconds. Huh? Okay. So I'll have to take the interval like this now, that t is greater than 1.5 and less than equal to 3 seconds. So this is the interval for which v is decreasing. So this is the information that application of differentiation and calculus tells us in terms of application of derivative over here. So finally from this, what I realize is that for the given relation, which was this, between 0 and 3 seconds, the particle is accelerated, that is v is increasing from t equal to 0 to 1.5 seconds. Okay. And the particle is decelerated, that is v is decreasing from t equal to 1.5 to 3 seconds. What's happening about after 3 seconds, we'll not worry about over here, because the question has specifically given us the range of time from 0 to 3 seconds. Okay, it's actually quite interesting what's happening after 3 seconds, but we'll keep that for another example when we come to kinematics. Here we will just talk about this situation. So from 1.5 to 3 seconds closed interval, this is what is happening. The velocity is decreasing in magnitude. Okay. So this is a simple example of how the algebraic sign of the derivative, whether it is positive or negative, gives us information about the nature of the function, whether it is increasing or decreasing, and how we can use that for physical parameters in a particular situation. Like the physical parameter of velocity versus time, the rate of changes gives us the information about the acceleration. So positive means that it is accelerated motion with speed increasing. Negative means that it is decelerated motion with the magnitude of velocity or speed decreasing in this particular case, like this. Okay. Now, next thing we will look at is more about application of derivative. Okay, not just that it gives us information about the increasing and decreasing nature of the function, but it gives us more information about the local maxima and the local minima also. Okay, so as we're talking about local maxima and minima, so if the behavior of the function at a particular point is such that sort of reaches a peak, okay, so the function is increasing up to a certain value of x in the domain, and it sort of peaks at that point, and after that point it tends to dip, or the function tends to decrease again, then the behavior of that function is such that we say at that point there is a local maxima, like the point A that we had drawn earlier for this function. So it has a local maxima, which I'm denoting with L max, which is local maxima. And at the point B, precisely where it's reached that dip point, where it's reached a minimum within a local neighborhood of domain points, that is called the local minima point. Okay. So we had already seen that the function, it was increasing for x less than a, and it was decreasing for x greater than a. But at the point x equal to a, it has the local maxima, which means that the derivative of the function is equal to 0 at x equal to a. In other words, for y is equal to fx, we denote dy by dx, or derivative of the function, with the short form f prime x. So we're using that over here. So this becomes the condition, one of the conditions for local maxima, that at that point you can see that if we draw a tangent, it will be a flat line, it will be a horizontal flat line parallel to the x-axis. But then that again will happen over here also. So the slope of the tangent drawn at the point x equal to a is equal to 0. But what will also happen is, because the function is going from a nature of increasing to decreasing, so you can see that the second derivative, or the rate of change of the derivative, that is f prime x, that will be what kind of a quantity? It will be negative, because it's going from positive to 0 to positive. Positive to 0 to negative. The slope of the tangent was positive just before a, it's 0 at a, and then it's negative just after a. So the derivative function f prime x, it has a decreasing nature. Rate of change of f prime x is negative. That means its derivative, that is differentiation of the first derivative, or what we call the second derivative, that should become negative. So second derivative, which is denoted by d2y by dx square, or in short as f double prime x, that becomes a negative quantity at x equal to a. So this gives us the proper condition for local maxima at a given point. Okay, so I'll just summarize this. Take a look at this once first, then we'll summarize this, that how exactly we investigate a point for local maxima. So first of all, the slope at that point should be 0, because it's reaching a peak. So derivative should be 0. And secondly, the slope should be changing from a positive value before that point to a negative value after that point. So it's going from positive to 0 to negative. So the slope itself should have a decreasing nature, or the derivative of the function f prime x should have a decreasing nature. So its own rate of change, that is differentiation of f prime x, the derivative should be negative. So that is nothing but second derivative should be negative. Okay. So this gives us the condition for local maxima at a point at x equal to a. The derivative of the function at x equal to a should be 0, and the second derivative of the function at x equal to a should be a negative quantity. Okay. Now in mathematics, there are more complex functions where the second derivative might become 0, and it's more, then one has to do more investigation. But at this particular point of time for our physics applications, this is sufficient because it will cover most of the type of functions that we will encounter in our physics applications. We'll be able to understand the local maxima point by making use of this. Okay. Now, likewise, if you look at the local minima point at x equal to b, we saw in that graph above, the function has a local minima. Okay. That is because, again, what is happening is that the slope at x equal to b, that is f prime x at b, is 0. Okay. And the slope at x less than b is negative, and at x greater than b it is positive. Okay. So if this was that dip point where x is equal to b, so you can see that the tangent drawn at the point b, it will have a 0 slope, but the tangent drawn just before b, it will have a negative slope, and the tangent drawn after b will have a positive slope. So the derivative of the function is increasing in nature at x equal to b. So that means the rate of change of the derivative, sorry, of the single derivative, not the double derivative, the rate of change of this derivative function f prime x, which gives us the slope of the tangent, that should be a positive quantity. So in other words, second derivative should, or what we denote as d2y by dx square, that quantity should be positive. So that becomes a condition for local minima. So the condition, to summarize, the condition for the function fx to have a local minima at x equal to b some point is that the derivative of the function should be 0, and the second derivative of the function should be positive. Okay, so again, like we discussed for local maxima, this suffices for most of the simple type of function. There might be some complicated functions where second derivative becomes 0, and there we require some more complex techniques like nth derivative test, etc. But that's not required over here for us in our immediate applications. Okay, so let's look at a simple example of this. Let's say we have the function y is equal to sine square x minus sine x, with x ranging between 0 and 2 pi, and we want to find the local maxima and minima. So we will just use that condition that the function being sine square x minus sine x, okay, the derivative of the function is given by differentiation of this term. Okay, and when you apply the chain rule and everything here, this will become 2 sin x into cos x minus cos x. Okay, so this is our derivative. We can write it in a different way also, but this is fine for now. And our second derivative, or what we write as f double prime x, is derivative of this. So that is differentiation of 2 sin x cos x minus cos x. Okay. Now, before we differentiate this, we can just use a trigonometry formula here, that 2 times sin x into cos x is sin 2x. So that will just make the solving part a bit easier. And next, we can differentiate this again by using chain rule. So derivative of sin is cos, but that has to be multiplied with the derivative of 2x. So that is 2. Okay. Minus the derivative of cos, which is minus sin. So this will become 2 cos 2x plus sin x. Okay. So this is what our second derivative is becoming. F double prime x is equal to this. So notice that these are the two things we need to investigate for local maxima and minima. These are the two things that we need over here. So I will just show you the whole function and the working till this point once more. Then we will calculate the local maxima and minima next. Okay, so as we can see, for the condition of local maxima, we need to make the derivative 0 and the second derivative negative. So for local maxima, derivative should be 0 and second derivative should be negative. Whereas for local minima, derivative should be 0 and second derivative should be positive. So let's figure this out, how this is happening here. So f prime x we had just seen was 2 sin x cos x minus cos x. So that means f prime x being 0 means 2 sin x cos x minus cos x should be 0, which we can factorize like this now. So it means that either cos x is 0, which means that x within that domain that we have taken would be pi by 2 and 3 pi by 2, or 2 sin x minus 1 should be 0. And that would imply that sin x is equal to half. So that would imply that x is equal to either pi by 6 or 30 degrees, or 5 pi by 6. Sorry. Yeah, 5 pi by 6 or 150 degrees. 30 degrees, 150 degrees, 90 degrees, 270 degrees. Okay. So we are having so many turning points. Okay. So our turning points are the points where f prime x is 0. So in this case, they are pi by 6, pi by 2, okay, 5 pi by 6, and 3 pi by 2. So all in all, there are these many turning points. There are 4 turning points within the domain. Okay, because the domain was 0 to 360. We had taken 0 to 360 or 2 pi. Okay. Now we need to find the second derivative. And second derivative of the function, that was how much? That was 2 cos 2x plus sin x. 2 times cos of 2x plus sin x. That is nothing but the derivative of this term. So that's like this. Okay. So now let's investigate. So we can see that f double prime of pi by 6 is how much? It is 2 cos pi by 3 plus sin pi by 6, which is 2 times cos 60 plus half, sin 30. So that is 3 by 2. But more importantly, it's positive. Okay. Then similarly, second derivative at pi by 2 or 90 degrees is 2 cos pi plus sin pi by 2. So that is 2 into minus 1 plus 1. So that is -1. So that's a negative quantity. Then again, second derivative at 5 pi by 6 is 2 cos 5 pi by 3 plus sine 5 pi by 6. So that will become 2 times root 3 by 2 plus half. Okay. Sorry, that becomes half. Okay. 2 cos 300. So you can see that cos 5 pi by 3 is cos 300 is equal to cos pi by 3, which is equal to half. So that's again a positive value. And likewise, f double prime of 3 pi by 2 will be equal to 2 cos 3 pi plus sine 3 pi by 2. So that will be again 2 into -1, and this time -1. So that will be -3. So that will again be a negative quantity. So we can see that the two turning points at which the derivative is positive, these two, okay, they will become local minima. And the two where it is negative, they will become local maxima points. So let's just put together this information. So we can see that for the function sine square x minus sine x, we saw that f prime x is equal to 0 and second derivative is positive at x equal to these 2 points, pi by 6 or 30 degrees and 5 pi by 6 or 150 degrees. Okay. So therefore, the function has a local minima of f of pi by 6. So that is sine square pi by 6 minus sine pi by 6. So that is 1 by 4 minus half or minus 1 by 4. Okay. This is the local minima at the point x equal to pi by 6. Okay. And again fx has local minima of f of 5 pi by 6, which is again going to be the same thing actually, because that sine function is same. So this will again be the same thing. It will have the same value, 1 by 4 minus half. So it has a local minima of, it has a local minima of this much again at x equal to 5 pi by 6. So that is as far as the local minimas are concerned. Okay. So you can just review this part a little quickly and we will move on to the local maxima. Okay, so thereafter we will look at the other two turning points, and we'll see that those points are where we have the local maximas, and we'll calculate the maximas. Right. So as I said, now if we investigate the other 2 points, okay, you can see that the function there will be such that, so at x equal to the 2 points where we are getting local maxima, they are pi by 2 and 3 pi by 2. So there is a local maxima which is equal to the value of the function at pi by 2. So that is 2 squares, 2 sine square pi by 2 minus sine pi by 2. So that, as you can see, is 1. Okay. And then again at x equal to 3 pi by 2, we have the same thing, that derivative is 0, second derivative is negative. Okay. So we have a local maxima which is equal to this much. Now, interestingly, this will have a different value because sine 3 pi by 2 is negative of 1. So this value will in fact crank up to plus 3. Okay. So the local maxima at this point is plus 3 at x equal to 3 pi by 2. Whereas the local maxima at pi by 2 is so much. So we put together all this information. It gives us very interesting aspect about the nature of this function. That in that particular domain of zero to 2 pi, we're looking at the function 2 sine square x minus sine x. Okay. You can see that it was having local minimas of minus 1 by 4 and again minus 1 by 4 repeated at pi by 6 and 5 pi by 6. So it was having a local minima of minus 1 by 4 here. And again, a local minima of minus 1 by 4 here. So it will be 5 pi by 6. Whereas it had a local maxima of 1. That's, let's say, somewhere here. Here. And it had a larger local maxima. So let me just try and adjust this a little. So that I can draw a more accurate version of the graph. Right. So it has Now this kind of a value at 3 pi by 2, it has a value of plus 3. So let's say that takes it somewhere here. So this is going to be now the graph of the function. I'm going to try and draw a rough sketch of the graph. You can see that at 0, the value of the function is 0. Then it dips to this minima. Then it increases to this local maxima here. Then again at pi, you can see it will become 0. So probably has a more relaxed kind of slope here. Kind of something. Then it increases to this value here. And then dips to this. So it has some kind of a nature like this. Roughly speaking, the graph would be something like this. Okay, slight correction over here. The value of the local maxima, the function was not 2 sine square x minus sine x. The function was sine square x minus sine x. So here, this has to be sine square pi by 2 minus sine pi by 2. So this local maxima will actually give us 0. Okay. So I'm just going through this again. So just incorporate this small minor correction, that the function itself was sine square x minus sine x. Okay. So when we are looking at the point pi by 2, all this is all right. Derivative is 0, second derivative is negative, but the value of our local maxima that we'll get will be 1 minus 1, that is 0 now. And similarly, at the point 3 pi by 2, derivative is 0, second derivative is negative. But once again, this should not be there. This should not be 2. So the value will change slightly, and accordingly, our graph will also have to be modified. So we'll do that. Okay. So this will just be sine square 3 pi by 2 minus this. So it's minus 1 square minus of minus 1. So this value will become 2. Okay. So our local maxima is equal to 2 at x equal to 3 pi by 2. Okay. So we will just incorporate that here. Here also you can see the function that we had taken was not 2 sine square x, it was just sine square x minus sine x. So coming back to that here, you can see that you just make a bit of a change to the graph. So it will have a local maxima of 0 at pi by 2. And again, it will have a local maxima of 2, okay, plus 2. So that's this value here. At the point 3 pi by 2. So these are the local maximas, these 2 points. This point is not going to be significant anymore. So anyway, so coming back to the graph, see that this part of the graph was like this, starting from 0. Then it increases to 0 here at pi by 2. Then it decreases to minus 1 by 4 again. And then increases like this to 2. Then continues to decrease. So this is roughly speaking how the graph will look. So you can see that we have local maxima here, local maxima here, and we have local minima at this point. Once again, local minima at this point. Okay. So this is about this particular function and understanding its behavior, understanding its local maxima, minima, etc. using the calculus concept or the derivative application concept, application of derivative. So that's an interesting, though somewhat slightly complicated type of application of local maxima and minima. Now let's also understand a more common type of application in physics where we use local maxima minima concept. So we know the relationship between force and potential energy, the internal conservative force and potential energy. So if we have a one-dimensional system along the x-axis, so our potential energy becomes a function of x in that, and the internal conservative force F is equal to minus du by dx. So this is a concept that you would be familiar from the concept of work energy and work energy theorem. So let's look at an example based on this. So suppose we have a system with only internal conservative force acting on a particle along the x-axis such that its potential energy is given by the relation where x is in meters and the potential energy is in joules. So this is the information that is given to us. Okay. Now, if in addition to this, it is also given to us that at the point x equal to 0, the particle has a kinetic energy of 10 joules. The particle has a kinetic energy of 10 joules at the point x equal to 0. So we want to find the maximum and minimum potential energy that the particle will have during the motion, that is, okay, and the maximum kinetic energy the particle will have. And also we want to find out the locations of any stable and unstable equilibrium points. So just make sure you pause the video and understand the question properly once. We will discuss about this. In my video, we'll discuss immediately about it, but try to understand the question itself and the concepts that we'll be using in the question, like the relationship between internal conservative force and potential energy, and the fact that there is only internal conservative force acting, which means that we can apply conservation of mechanical energy over here. The system will have a conservation of mechanical energy because there's no external force and no non-conservative force acting on it. and we have the relation of potential energy, and we are given the kinetic energy at a particular point. So from that we can find the total mechanical energy, and from that, by using conservation of energy, we can understand how the kinetic energy and the potential energy are individually varying with position. So those are the concepts that we'll be using over here. Furthermore, when it comes to the equilibrium points, okay, we'll understand that equilibrium points are points where force should be zero. That means du by dx should be zero. But at the same time, the stable one is where the potential energy has a local minima. Okay, so at a stable equilibrium point, the potential energy should have a local minima. Okay, whereas an unstable equilibrium point will be a point where the potential energy has a local maxima. So we will use these relations also over here. That at the point of unstable equilibrium, if any, then the potential energy function should have a local maximum. Okay. So let us look at this question next. So what we'll do, kinetic energy plus potential energy, which is the total mechanical energy, will be constant. Because the question has told us that only internal conservative force is acting on it, acts on the body, you know. So we can see that at x equal to 0, the potential energy is minus 5 joules, that you can see from this relation here, and the kinetic energy is 10 joules, which you can see from this relation here. So the total mechanical energy we are getting as how much? We are getting it as 5 joules. Energy is 0. Potential energy will be maximum. Okay, because this is the minimum value of kinetic energy. And when kinetic energy is maximum, potential energy will be, that is what we'll understand next. Okay, so for that we will investigate this function of potential energy which is given, u is equal to x to the power 4 minus 2x square minus 5. We'll see that du by dx this much. Okay, and second derivative this much. Okay, so you can see that du by dx is equal to 0 at x equal to 0, 1 and minus 1. So these are our turning points. Okay, and we can see that second derivative is equal to, we can see at x equal to 0, second derivative is minus 4. Okay, at x equal to 1, second derivative is plus 8, and at x equal to minus 1, second derivative is again plus 8. From this value you can see, substitute x as plus minus 1 here. So immediately you can understand that this function will have local maxima. Local maxima, it need not be the global maxima, at x equal to 0, and local minimas at x equal to 1 and x equal to minus 1. And what will be the value of that local maxima? The local maxima will be equal to the value of the function at 0. So that is 0 to the power 4 minus 2 into 0 to the power 2 minus 5. So it's minus 5 joules. That is the local maxima at x equal to 0. Whereas the function will also have local minima at x equal to 1, local minima will be 1 to the power 4 minus 2 into 1 square minus 5. So that is how much now? It is minus 6 joules at x equal to 1. And similarly at x equal to minus 1, the local minima will be minus 1 to the power 4 minus 2 into minus 1 square minus 5. So again that local minima will also be symmetric. It will be minus 6 joules. Okay. So we're getting some kind of idea about the graph of the potential energy function. We are getting the idea about the graph of the potential energy function, that it will be something like this. It will have a value of minus 5 at 0, and then at plus 1 and minus 1 it has a symmetric value of minus 6 joules. So in other words, the potential energy graph should become something like this now. Should become some kind of symmetric graph like this. Okay, now you can also see that kinetic energy is 0 at what value of x? So kinetic energy plus x to the power 4 minus 2x square minus 5 be equal to 5. So this is 0 implies that x to the power 4 minus 2x square minus 5 should be equal to 5. Okay, kinetic energy is equal to 0. This implies this, or x to the power 4 minus 2x square minus 10 is equal to 0. So this will give us, so if we do this, we will get x square's value as 1 plus root 11. Solving this like a quadratic equation for x square, you substitute x square as some new variable z. So you have z square minus 2z minus 10 equals to 0. So you solve that and you'll get this, which means that this x square will be approximately 4.32, which means that x will be approximately 2.07 plus minus of. So those will now become like boundaries of this, okay, because the potential energy function, it will have to behave in such a way that it has a certain range. It can't go beyond a certain point, because at that point the kinetic energy is becoming 0. So the potential energy will have a certain maximum value here, where at these 2 points which we have just seen here, 0.07, or symmetrically on the other side minus 2.07, the kinetic energy becomes 0. At these points, kinetic energy is equal to 0. Okay, and therefore the potential energy will be equal to plus 5. That is the maximum potential energy. Whereas at these 2 points, so you can see over here that at x equal to plus minus 2.07, the kinetic energy is minimum and the potential energy is maximum, which is equal to the total energy. Whereas on the other hand, at the other 2 points, you can see at x equal to plus minus 1, the potential energy is having the minimum value, minus 6 joules. This is the minimum. And therefore, the kinetic energy will become 11 joules, which is the maximum value. Okay, because the total mechanical energy, remember, kinetic energy plus potential energy is 5 joules. Okay. So when the potential energy reaches the minimum value of minus 6, the kinetic energy automatically has to become plus 11 because total energy is this much. Whereas when the kinetic energy is minimum, that is 0, the potential energy has the maximum value, which is equal to E. Okay. So these 2 points are coming from this, that U's minimum value plus kinetic energy's maximum value is equal to 5 joules. Now we saw from our investigation earlier that U's minimum value is equal to minus 6 joules. So from that we are getting kinetic energy's maximum is how much? It is 11 joules. Right? Whereas similarly here we are seeing kinetic energy's minimum value plus potential energy's maximum value is 5 joules. Now kinetic energy's minimum value is 0. Logically, that when the particle comes to rest. So from that we are getting that the potential energy is maximum value is equal to 5 joules, and we just saw that that is happening at x equal to plus minus 2.7. So we've actually solved a few more things than was required in the question also. We have found the range of motion. For this value of kinetic energy given at x equal to 0, what happens is that for the given kinetic energy of 10 joules at x equal to 0, the particle will keep moving, that is oscillating back and forth between x equal to plus minus 2.07. And every time it oscillates, at some point of time it will have maximum kinetic energy, which will be 11 joules when it's passing through either plus 1 or minus 1, and at some point of time it will have maximum potential energy, which will be plus 5 joules when it is reaching the end points, which are x equal to plus minus 2.07. Okay, so again this is a fairly interesting but at the same time mathematically involved kind of application of maxima minima. And this is just to show you like the scope of the concept of maxima minima from calculus itself in solving physics problems. Okay, so this is basically more a problem of work energy, where we are using the conservation of energy principle for a system which has only internal conservative force, but is demonstrating how we have to use the techniques of calculation of maxima minima to come to the conclusion about the numerical values. Okay, so that is about maxima minima. Okay, and more or less with that we complete our discussion about the applications of differential calculus and differentiation. Now next thing we move on to is integration, which is the second part of, or the second set of operations in calculus. Okay. So we move to integral calculus and its applications. So as you know, the integral calculus concept starts with the basic operation which is called indefinite integration. And indefinite integration is an operation that results in calculating what is called antiderivative of a function. So the purpose of this operation, integration of any function with respect to its variable, is to give us what is called the antiderivative of the function. Okay. So integration of the function fx with respect to the variable x gives us the value of ix, which is the antiderivative of fx. So antiderivative means that if we were to differentiate this function ix, which is the antiderivative, we will get the original function we were integrating, which is fx. This is the meaning of the term antiderivative. So I'm sure you're all aware of this, and pretty simple. So let's look at a simple example if we were integrating, for example, cos x, now we know that the differentiation of sin x is equal to cos x. Okay. So that also tells us that the differentiation of sin x plus any arbitrary constant, c is any real number constant, this will also give us cos x now, because differentiation of a constant is 0. So that now tells us, this information here now tells us that, okay, the antiderivative of cos x should be given by a general function sin x plus c. Okay, why this is the antiderivative? Because we now know that if we were to differentiate this function, we would get the original function which we are integrating, which is cos x. So we'll say the antiderivative of cos x is the function sin x plus c, and precisely actually it's a family of functions, sin x plus any constant. So it could be just sin x alone, it could be sin x plus 1, it could be sin x plus 1000, sin x minus half, sin x minus root 3, whatever it could be, it's whole family of functions where the constant c can take any arbitrary value. So this is the process of indefinite integration, and it's pretty simple to that extent, because it's like a inversion of the process of differentiation. Okay, so let's look at some of the formulae and properties for indefinite integration. So the first basic formula for any type of algebraic function is, if we are integrating x to the power some real number n with respect to x, okay, then the antiderivative is given by the formula x to the power n plus 1 upon n plus 1 plus c. So here what happens is that n can be any real number excluding the situation where the denominator becomes 0. Okay, so it's any real number excluding n equal to minus 1, because then the denominator becomes 0. So for example, if I'm just integrating x cube, it would be given by the formula which would result in x to the power 4 divided by 4 plus c. So this function x to the power 4 plus x to the power 4 divided by 4 plus c, that becomes the antiderivative of this function, which is x cube. Okay. If I'm integrating 1 by root x, for example, okay, so that can be expressed as x to the power minus half. So that would become x to the power minus half plus 1 upon minus half plus 1. So that would be x to the power half, or 2 root x plus c. If I'm integrating, let's say, root x, this would be, which I could write as 2 by 3 x to the power 3 by 2 plus c, or I could even further write it as 2 by 3 x root x plus c. So these are some basic examples of the application of this power rule. But remember, n should not be minus 1. For any other value of n, we can use this formula. It should not be minus 1. So let's understand what happens when it's minus 1. For n equal to minus 1, the antiderivative of the function 1 by x, that is given by the simple formula ln x plus c, because we know that the differentiation of natural log of x is 1 by x. So naturally, the antiderivative of 1 by x becomes natural log of x plus c. Okay, so that is the exception rule that you should remember. Along with this, there are also the simple properties. Like if we are integrating a constant with respect to x, c is a constant, then integration of this, it becomes cx plus some new constant, let's say k. K is the any real number constant. Then if we are integrating a constant multiplied by a function, so we can take the constant outside and integrate the function. So for example, if we want to do integration of 5x squared, so first step we'll take the 5 outside, then we will use the formula that we've seen earlier, x to the power n plus 1 upon n plus 1. So as you can see, this will become 5 by 3x cubed plus c. So very simple, nothing complicated about these. Then similarly, another important property is that the integral of the sum of two functions can be expressed as the sum of their integrations. So for example, we are integrating, let's say, something like this. So we can express this as this, and then further we can express this as this. So become 4 by 3 x to the power 3 by 2 minus 1 by x plus c. Or we can also express that as 4 by 3 x root x minus 1 by x plus c. So these are some of the examples of the basic properties of integration using this algebraic formula. Now let's also see some of the trigonometric formulae. So integration of sine x given by minus cos x plus c, because we know that derivative of cos x is minus sine x. So the derivative of minus cos x is plus sine x, that's right. Similarly, integration of cos x is sine x plus c, whereas the other ones are a little bit more complicated to demonstrate. This is natural log of sec x plus c. That happens because if you were to differentiate natural log of sec x using the chain rule, that would become 1 by sec x into differentiation of sec x. So that would become 1 by sec x multiplied by sec x tan x. So that would become tan x, okay, which is the integral. So that's why you can see the justification of this. Okay. Similarly, the other three formulae, integration of cosec x is minus ln cosec x cot x plus c, and the integration of sec x becomes natural log of sec x plus tan x, and integration of cot x becomes ln minus ln of cosec x plus c. So frankly speaking, we don't always need so many formula in physics. It's more the basic ones that we go after: sine, cos, etc., tan, then the power rule earlier, x to the power n, and some of the properties and characteristics of integration. But again, for the completeness of your knowledge and applications, you should know at least all these formulae. And in addition to this, you also have integration of exponential function, gives us the function itself. Because derivative of exponential function is the self function. So antiderivative is also the self function plus c, that kind of situation. So this is about the basic formula of integration. Okay. So once again, I will be focusing more on the applications of integration rather than the basic formula. So let's look at an example or two. Then we'll come back to more techniques in integration. So suppose we had a situation like this, that we have sort of a cylindrical rod that we made, but the material has non-uniform density. So we have made, let's say, a solid cylindrical rod. So the shape is symmetrical. It has a uniform thickness everywhere, but at the same time, while the shape is uniform, what is happening is, let's say, the density of the cylinder is not uniform. So you have to color code the density. So you can see it's getting darker as you go. Means the density is increasing. So we have a solid cylinder which has a radius of r, therefore diameter of 2r, and a length L. But it is anisotropic. That means it is not uniformly dense. It has an anisotropic mass distribution such that its density is a function of x, such that it's where inside the cylinder, if we take any point which is at a distance of, let's say, x from this end of the cylinder, any point which is at a distance of this end of the cylinder, at a distance of x from this end, it will have a density given by this. Okay, so this is the density at any point P, which is at x from one end of the cylinder. Now we want to calculate the total mass. So rho naught is a constant over here. So let's say given that this constant rho naught is equal to 2 gram per centimeter cube, gram per cc. Okay. Radius is, let's say, 2 centimeters, and the length is, let's say, 20 centimeters. So you want to find the mass. You want to find mass m of the cylinder. Okay. So the thing is, see, generally speaking, if the density were constant, if density had been uniform, then we would have used the relation that mass is equal to density into volume. So here it would have become pi r square L. But here the problem is that's not the case. The density is variable. Okay. So we have to use integration. Application of integration, what we will do is slices like this. We have sliced it over here. We've taken a thin section of the cylinder of thickness dx, which is at a distance of x from this end. So at a distance of x from this end, we've taken a thin slice. And next what we will do here is we will say that the mass of that slice will become density into volume of that slice, where its area into thickness is the volume of the slice of function into the volume of that slice, which is pi r square into dx. Okay. So the total mass will come as the summation of all these slices by integration. So we are summing up the masses of all these slices by using integration. Okay. Starting from the slice over here, which is at x equal to 0, right up to the slice over here, which is at x equal to L. So the limits of integration will be x equal to 0 to x equal to L. So m becomes, take the constants outside, and you're left with this integration 1 plus x by L from x equal to 0 to x equal to L. Okay. So the integration further results in, you can see the integration of 1 plus x by L, that can be expressed as the integration of dx plus integration of x by L dx. So this will just give us x, and this will give us 1 by L in x to the power 2 divided by 2. So this integration separately is x plus x square by 2L plus c. So when we put the limits, we don't need to write the integrations constant. And instead, we'll just put the limits x equal to 0 to x equal to L. So we see the upper limit minus the lower limit will be 0 only. Okay. So the total mass will become 3 by 2 rho naught into pi r square into L. And now in this, we can just substitute the values which we had. We can substitute density as 2 grams per cubic centimeters. That is the same thing as 2000 kg per meter cube. Okay. We can substitute R as whatever it was, I think 2 centimeters and 20 centimeters. So substitute all this here and we will get the mass in kgs if we substitute in SI units. Okay. So this is an example of the application of integration in an actual physics problem, how we set it up. Okay. It's all about being able to take the differential element, which in this case is the slice of the cylinder, and expressing the physical parameter. Like in this case, we are calculating mass. So mass is the physical parameter which we have to express for that thin slice of the differential element, and then integrate it for the whole thing. Okay. So this, as you will know, is like an important part of the application of integration in various branches of physics, like straight from mechanics to, from kinematics and mechanics to center of mass, rotational mechanics, things like moment of inertia. Then later in the chapter of gravitation, in the chapter of fluid mechanics, a lot of these places, these things become important. So this is where we'll conclude today's session. Okay, and next time we will pick up some more examples of the application of definite integration, and we'll discuss about definite integration also in more detail. So that's it for today's session, people. Hope you all have enjoyed the session and have followed most of the things. Until the next time, that's it from my end. Wish you all the best.